All right, we're gonna go ahead and get started now. If anyone else is late, that's their problem. All due respect. Okay. So,
Right.
yeah, go ahead.
Start off with question 1. So this is the exam 3 review, by the way. I already sent this out. No, if y'all didn't see this, then check your emails once again, because I didn't send it out. So anyways, question 1. A formal charge on oxygen in dimethyl ethers, so CH3, OCH3 is. What's the first step in solving this stuff? How would you draw this?
Know which one's the central atom.
Which one's central atom?
It's gotta be a carbon.
One of the carbons.
Really smudge when I thought all of the heteros always determine mine.
Is the least electronegative the usually the
Or no,
central
it'd be
atom?
more close. It's the least.
Least electronegative is the central atom?
Yeah.
And that is indeed true.
That is indeed true.
Proteins in the middle.
That is indeed true for most things, but this is an ether. An ether functional group has an oxygen between 2 R groups. Those R groups can be really long chain, or in this case, they can just be 2 methyl groups. So CH3 is connected to the oxygen.
And in case you don't care about OChem at all, look at how the Lewis structure is drawn out, or the atoms are drawn out. Usually what they'll do is they'll draw out the atoms in the exact order they're connected. So the CH3 is next to an O, which is right next to a CH3. So that's how we should draw it out. So I'm gonna go ahead and do that. Over here, over here. Okay, this is our structure. Now what do we do to calculate the formal charge?
Real electrons minus. 1 is pairs minus. 1 divided by 2. 1/2, yeah.
So what is, or how I like to do it right is number of valence electrons minus the number of electrons it owns. How much it owns means like, what's it called? How much it owns is like how many electrons are surrounding it, so to speak. So there's 1, 2, 3, 4 electrons here, right? Just due to the lone pairs. And then there's 5 right here and then 6 right here, because each of those oxygen only contributes 1 electron to the bonds. There's a total of 2 electrons in a bond, right? And then the carbon has 1 electron in the oxygen. So it's 1 and 1. So how many valence electrons does oxygen have? 6, exactly. So then
Formal charge of 0.
yeah, because it owns as well 6 electrons. So it's 6 minus 6, and then you get a formal charge of 0. Another shortcut you can take is notice how there is no charge overall in this molecule, right? Like there's no 2 plus, 3 plus, anything like that. So because of that, you can say with confidence, with chest, high with pride, whatever you want to call it, that all atoms in the structure have a 0 formal charge. Because here's the thing, the charge, like say you have nitrate, NO3 minus, the charge right here, the -1, the -1 right here actually contributes to the formal charge of the overall molecule. So what it's saying is that the overall charge of the molecule is equal to -1. So it's the same case here, right? CH3, OCH3. Do you see any charges on here at all? No, right? So because of that, you could say that everything here is 0.
And also just remember that every time oxygen has 2 bonds, it has a formal charge of what? If it has 1 bond, it has a formal charge of what? -1, right? And if it has 3 bonds, it has a formal charge of what?
+1.
+1, right? So exactly. So those are 3 things you can also just kind of remember. So you just have to draw it out, look at it, 2 bonds, oxygen has a formal charge of 0.
All right. So with that being said, any questions about that in the room or on the Zoom? Right, cool. Move on to question 2. Draw all possible resonance structures all possible, like everything that's there, I want it. For the sulfide ion, SO3, 2 minus. What would be the first step?
Sulfur in the second.
Sulfur in the center, okay. Let's actually go a step back. Let's count the number of valence electrons this has. So sulfite, right, SO3, 2 minus. How many total valence electrons does this have? 6. See, 18 plus 6 is 24, 24 plus 2, 26. Remember, right, the -2 actually adds 2 electrons. So, right, the sulfite, now, as somebody said, the sulfur is indeed in the center because it's the least electronegative, and then oxygens are all over here surrounding it. Now, what's our next step?
If I could, the terminal electrons, the whole 3 times 8 each other.
And indeed do that. And as a matter of fact, let's do it. So 3 times 8 is 24, right? And then subtract that by 26. So 26 minus 24 is 2 valence electrons. What does that mean? Divide that by 2, that gives you 1. What does that mean?
Maybe a lone pair on the sulfur.
Yeah, there's a lone pair on the central atom. Let's not draw all that in yet. Let's do that last. So let's go ahead and connect our bonds, to make all the bonds. So sulfur to oxygen, there's 3 bonds made here. How many total electrons did that use?
6.
6, exactly. So 26 minus 20. So not 20, sorry, 26 minus 6, that's the total of 20. Now, what do we do next? What does everything need to be satisfied?
8 electrons.
So how many, all right, let me ask this. How many electrons does, one. All right, technical difficulties aside, how many how many valence electrons does this oxygen need to be satisfied? Needs 6 more. So let's go ahead and put a 6 right here. Now, what about this oxygen? 6. Also 6, yeah. What about this oxygen? Also 6 again. And then how about the sulfur? 2 electrons. So what we can go ahead and do is let's write out all these electrons. Is since 6 plus 6 plus 6 plus 2, it's a total of 20 electrons, right? Everything's happy. So we can go ahead and draw that in. SO 1, 2, 3, 4, 5, 6. Right. Then we can go ahead and put a 2 minus. We're done, right?
I would say so, I'm not gonna lie, just because you said that.
You used to do like formal charge.
I think.
Do you have to do formal charge? That is an excellent question.
Oh, yeah, it
Isn't it
says
with-
all possible resonance structures.
Is it with oxy ions, the charge indicates how many like single bonds they need?
Yeah, that's what.
Yeah, the charge does indeed indicate how many single bonded oxygens there are. Great observation. So 2 minus, right, means 2 single bonded oxygens. But before that, right, what's the one rule that trumps octet? One drawing our little structures. Formal charge, yeah. Formal charge is always greater than octet. The formal charge is greater than, so what is the formal charge on this oxygen?
7 plus.
Plus 1?
Yes, 6 minus 7.
It's my 7 is plus 1.
Oh, sorry.
-1.
-1, there we go. Absolute decimals. And then what about this oxygen?
-1.
-1 again. Now, finally, this oxygen,
-1.
another -1. So does this add, or actually, what about this sulfur? That is indeed plus 1. But is this a good structure? Deal?
No, I mean the formal charge straight.
Can we make it better? How do we do that?
I have a double bond.
How do you add a double bond? Move into which oxygen?
Either, any.
Does it matter? not indeed matter. So what we can go ahead and do, let's just say we're gonna move it to this bottom oxygen. So to make the formal charge better, these electrons, right, are gonna go over here. And then we can just erase one of these lone pairs because we don't need to be with that. So, right, our final structure would be looking something like this, S double bonded O.
I think you accidentally did something. Look at the screen. Turn around.
You're not sharing your screen.
Ended unexpectedly, just like, okay. Like some professors are unexpected failures. All right, there we go. S double bonded O, and then we have two single bonded oxygens. Now let's try it out. Does this look better as a structure? So. Used to OChem where they don't make it do that, drawing in lone pairs. All right, anyways.
Now let's-
Oh, yeah, I can't do that. There we go. So, yeah, this is actually there, but the electrons go over there. So, right, what is your, so this is one structure, right? What's our, what are more structures we can draw? Yeah, just move the double bond to each oxygen. So it looks something like this. Here, here, I'm not gonna, just know that there are lone pairs here. I'm just not gonna try it for neatness sake.
So why is the sulfur still lone pair on it? If it's being part of double oxygen instead of the sulfur?
Wait, let's count up the total number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 21.
If it's S of something, 2 minus. I did.
So the lone pair on the sulfur is actually still there because what happens is, since we move this these electrons over, the electrons from the oxygen have to compensate for that somehow, so they'll put a lone pair back there. Because if you move these electrons, right, you'll have something like this with three lone pairs on this oxygen and a double bond. What's the formal charge on that?
Exceeding the octet first of all.
Yeah. Formal charge always trumps octet. So you're gonna go ahead and do is just move one of these lone pairs over back to the sulfur and then,
Why didn't you just do the oxygen?
I mean, I could have done that, but here's the thing with resonance structures. It's the same molecular formula, different arrangement of electrons. So to get like multiple different resonance structures, all you have to do is just move electrons around.
I'll do the next one.
And then final structure, right, is something like this. So it'll be this oxygen now, and oxygen here, and then also the. So any questions about that? Until I arrived to what I did. So NL3, sure. So NL3, right, would look similar to how we did this flat ion right here. It'd be nitrogen here, oxygen, oxygen, another oxygen. So then, right, you do your valence electrons, so that's 6 times 3 is 18, plus 5, that's 23, plus another 1, that's 24. Then, right, we're gonna go ahead and draw our bonds. So that 24 minus 6 is gonna be 18. Then, right, you need 20 total electrons to satisfy this entire thing, because oxygen, each of these oxygens needs 6 more, plus this nitrogen needs 2. So 18 minus 20, you're deficient 2 electrons. So now what you can go ahead and do is double bond one of these oxygens. And then single bond the rest. So what you get is NO, O, and then a double bonded O. That's right. That.
That's right.
Oh, I know.
That's right.
All right.
But could you explain why you do that? I know it needed a double one.
How I knew that I don't need a double bond? Because, right, so you have 18 electrons here that are left to satisfy this thing. Oh, wait. Yeah, so there are 20 electrons, right, total that you need to satisfy this NO3 minus rate. Is because there's 6 on each of the oxygen and then 2 for the nitrogen. So that's 20 total electrons we need, but we only have 18. So what does that mean? We're missing 2 electrons. And if we're missing 2 electrons, or
What we first did was figure out how many valence electrons we have, so. So he did was something like this. So how many valence electrons are there? There's 5, 6, 12, 18 plus the 5 from nitrogen. So 6, 12, 18, 23 plus 1, there's 24, right?
Yeah.
So we have 24 valence electrons. So those valence electrons, first you draw a bond to each one, right? And we use 6 electrons there, so that's -6. We have 18 left, and we know that we need, in order to fulfill the octet, we need 6 here, 2 here, 6 here, 6 here, right? Because each of these oxygens only has 2,
Oh, okay, yeah.
right?
Yeah.
So that's 6, 6, 12, 18, 19, 20, right? So we're gonna do -20, and we end up with -2. That means we're deficient 2 electrons, meaning we need to form a double bond somewhere. That double bond can only go in one place, between a nitrogen and an oxygen, right? Because you can't form a bond like this, right? You have to do something on the next, the neighboring atom. So that's when we put that there. So now we start our count again. So we started off with 24 valence electrons. We use 2, 4, 6, 8 in bonds. So -8 will give us 16. And now we need 6 here, 6 here, and 4 here. That's 6, 12, 4, 16. Nitrogen already has a full octet, so we don't need any more there. So -16 will give us a 0. And you should plug in all, or not plug in, put in all your lone pairs. Or, yeah. Okay. And that's how we knew we had to add a double bond, because we were deficient 2 electrons, right? Over here when we did the 18 - 20 to give us -2 electrons. And if you were to do the formal charge on here, each of these oxygens has a -1 charge. This one has a +1. The nitrogen has a +1 charge, meaning that the overall charge, let's just say that these 2 negatives and positives cancel out. So the overall charge is that -1 charge, which is why nitrate has a -1 charge.
also, right, you want the positive charge should be on the more electronegative atom. So,
Right, the
sorry, less electronegative.
Yeah.
Positive on the less electronegative. So notice how nitrogen, right, is less electronegative than oxygen. It has a +1 charge instead of the oxygen. If the oxygen had a +1 charge, then that molecule is crying out in pain, basically. It's one way to think about it.
Okay. If there's no questions, we'll go ahead and move on so we can get more questions. So of the 2 compounds below, which one is more polar? I don't know if y'all talked about this yet, but this is dealing with cis-trans double bonds and how that affects polarity. Does anyone have an idea? All right,
Maybe the first one.
we didn't solve number 3. What's number 3?
So bonding.
Oh, yeah, sorry, I didn't even realize that we solved it. We'll come back to number 4. So acetone looks like this.
It's just something to think about. Number 4 is something to think about at the moment.
So acetone looks like this. I'm not gonna draw out the hydrogens for simplicity. Well, they're there, but I'm not gonna do the whole stick figure thing. So it's asking, what is the bond angle between a what is it? CCO, so it's asking for this bond angle right here. Does anyone know what that bond angle is? In 120, why?
Because it's true.
All right, so she said it's trigonal planar molecular geometry, meaning that it's gonna have a bond angle of 120 degrees between all atoms. All right, so that's correct. It'll be 120. All right, back to number 4. Which one is gonna be more polar?
Are there carbons in between or not?
Yeah, they're carbon.
There are, right? And then,
So,
sorry,
so yeah, like this thing's a carbon, this thing's a carbon.
and
Yeah.
double bond,
Yeah.
This is a double bond. Yeah, so these are carbons right here.
and there's hydrogens attached to them.
There's one hydrogen attached to each.
Yes. So it could be dark. Oh,
Yeah, what do you?
This is more polar.
Okay. Okay, so which one is, Alex, which one is it? The second one, why?
Symmetrical.
What?
The way I think of it is like if you like turn it, like cut it in half, like less symmetrical. I guess.
More symmetrical?
Non-polar is more symmetrical, right?
I wouldn't even think about those. Yeah, yeah,
The fluorine is more electronegative, so it has a,
they're all fluorine though.
oh, the fluorine,
Yeah, see all the four Fs on, or two on each one.
like, wouldn't like that P part be a C, like carbon,
So you're saying the left or right one's more polar?
the right?
Okay, and that is true. Do you know why?
What, why, what is this structure called? Like, you know, Louis structure, what is this?
Okay, sorry.
That's called skeletal structure.
So this is called a skeletal structure where you don't draw out your carbons or your hydrogens. So if we wanted to, it would look something like this. It's not, it's kind of, you'll see why no one does this when we take over, right? Or it'd be,
I know this. Not very well, I know it.
okay, so these are, maybe looking at it now, it'll make more sense. I came in late today. No, I'm just kidding, what? I mean, sorry,
Well, fluorine is more electronegative, so on the right.
more electronegative than what?
than hydrogen. So on the right.
It's being tipped.
Yeah, they're doing like whole.
Yeah, so you have to, so because this is what we call a trans, or trans isomer. Where it's transit, like the substituents are transitioning from one side to the other, okay? Which is why it's called trans.
Trans means it's on opposite sides.
Opposite sides of the double.
Substituents are on opposite sides.
Directions.
Yeah.
Okay,
Because they're both going.
and this is called a cis, meaning it's on the same side.
Not exactly.
So
This is like.
you can, I don't know, yeah,
So cis is the same way.
okay.
Did you say the scripts?
So
This is on the
with
same.
this, the one that's gonna have be more polar is the one where there's not where there's a net dipole, right? I'm not sure if y'all learned about this. Yeah, some of y'all, okay, so the one that's gonna be more polar is gonna have a greater net dipole. We can kind of imagine that these two fluorines are pulling and tugging each other, tugging on each other in equal and opposite directions, meaning that there's not really gonna be a net dipole. You can kind of think of this, I don't know if y'all have taken physics, but you can kind of think of this one's kind of pulling it in this direction, right? And that one's pulling it in this direction. And if you were to do like the vectors and like you would do in physics, it would be like that and to the left, and this one would be up and to the right. So those would cancel out, leading to no net dipole. Whereas this one on the right side, it's going to be pulling it down and then to the right, or to the left, and this one's going to be pulling it down and to the right. So there's a net dipole. So these two, the ones pulling it to the left and right kind of cancel out, but there's a net dipole down. We can see that, right? Because they're both pulling down. Whereas this one was pulling up and this one's pulling down. So when you have cis isomers, those are going to be typically going to be more polar than trans isomers because you don't have that canceling out of the net of the dipole moments.
Why only typically? What are the exceptions?
Like, so like, if you have just something like this. Let's see, CH3. CH3, and H. Most things with like, just carbon and hydrogen aren't really like polar, they're really not polar, so there's no like polar bonds or anything.
Yeah.
So it'd be like a non-polar molecule. So, but once you bring in like electronegative atoms like fluorine, then you start seeing a polarity difference between the electronegativity of all the atoms, resulting in dipoles.
Okay.
Yeah.
How do you read skeletal structure?
How do you read skeletal structure? Yeah, so,
Like a lipid.
yeah, so every,
It's a carbon.
Okay.
Carbohydrate. Oh, something rises. Yeah.
like, You have a question regarding something like this?
Yeah, can you explain why it's not polar?
Which one?
The one you just drew with the seal.
This one?
The one you just drew.
Because it's like, so there's no polar bonds, right? Because the bonds here are carbon-carbon bonds.
CH is non-polar.
The CH is a non-polar bond as well.
So CC, so.
So there's no polar bonds, right? And what was your question?
How do you read skeletal structure?
All right, so like, you look at this, every little point or vertex, I guess you can say, is a carbon. So if we were to draw like a propane chain, which has 3 carbons, you would draw it like that. So you would have a carbon here, a carbon here, a carbon here.
Hydrogens as well, you don't draw those. It's kind of implied that this carbon, like that carbon right there has 3 hydrogens.
Yeah,
And then
this one right here, it's implied that it's a methyl group that has 3 hydrogens. This one in the middle, it has 2 bonds already, right? 1 to 2 other carbon, or 2 to 2 other carbons, this one and this one. Meaning that in order to fill its octet, it has to have 2 hydrogens, right? And then this one over here, this carbon right here, that only has this 1 bond. And carbon like to form 4 bonds, so it's kind of implied that it has 3 bonds to hydrogen.
So every time that there's a skeletal structure, there's gonna be some amount of hydrogens attached to a carbon.
Exactly, yeah, exactly.
this carbon wants to form 4 bonds, right? So because there's only 1 bond over here, then there's 3 more bonds it needs to form. So that you fill those bonds in with hydrogens.
Yeah, exactly.
What do you make fun of me for drawing benzene as a Lewis?
Exactly. No one draws benzene as a Lewis structure.
It's just a hexagon of 3 lines.
Okay, so I'll give you all just a couple seconds to think about which one is polar, and which one is more polar. And it's important to note that for this one right here, the reason that they're isomers is because that double bond that pi bond is going to restrict free rotation. All right, so that pi bond keeps these atoms in their spaces. Just like if it's cis, it's always going to be cis. You can put it in a bottle, put it on a shelf, and when you come back, it'll be cis. They'll never interchange from cis to trans because that double bond is going to restrict free rotation around these carbons right here, or this bond. Right, so looking back.
What do you all think about this?
Okay, so my idea is that they might be the same because without the double bond, the left one is able to be moved. So at some point.
Yeah, so what he said, this was kind of a trick question, all right? It's to help y'all realize that you can only talk about these trans and cis isomers when you have a double bond. In this case, there's no double bond between these 2 carbons right here. Thus, they can there's free rotation around this single bond, meaning at one point it can look like this, at the second, and the next second it can look like this. So they're both the same exact molecule, actually. There's no difference between these 2. It was kind of a little trick question to make sure y'all remember that this is only applied or can only be applied to double bonds, all right? Because those have restricted rotation around this area right here. Whereas this one, you can kind of rotate it around in like 30 or 300 or 180 degrees, I guess. And then you would end up with this thing right over here. So same exact thing. So the answer to this one is none. They're both the same. What is the correct Lewis structure for nitric acid? I'll give you all a couple minutes for this. It's a multiple choice question, so. And if you're on Zoom, you don't have to put your thing in the chat, okay?
Actually, please don't put your thing in the chat, otherwise everybody will see it.
Exactly. This guy. You're welcome, Michelle. It's Michael Jordan. Michelle. You get back to it. Oh my You have an answer, Audie? Interesting. Interesting.
Yeah, it's only supposed to. 4 to 6.
Okay. Do we have an answer? Sam, which one do you think it is? What? I with pride, I mean, say with pride. B? What are we thinking? Anyone? Okay, raise your hand if you think it's A. B? I with pride. I didn't see these hands. C. Interesting, okay. So we got D's and C's here. We can all agree that A is wrong, right? Because we know that the hydrogen should not be on the nitrogen, it would be on the oxygen. Okay, so off of that, A is wrong. There's another reason why A is wrong, but I won't.
Nitrogen has like 6 million electrons.
Yeah, okay, we're gonna go.
That nitrogen is crying out pain.
So looking at B and C. Looking at B and C, there's really, so you look at the formal charge and you're like, huh. I think to be the most stable, you want formal charges of 0. So you would choose C. But when you look at C, how many bonds does nitrogen have? It has 5 bonds, right? It has too many bonds, meaning what? Is that even possible for nitrogen to have 5 bonds? No. So C does not, he's drowning in electrons, right? Or it's drowning, whatever nitrogen wants to be, whatever nitrogen wants to be. It's drowning in electrons. So C is also invalid. The only reasonable structure for nitrogen would be B. And you see that nitric acid does not have a negative charge or a positive charge, and it's because these negative charges and positive charges cancel out to give an overall charge of 0. Don't cancel. I won't cancel anybody. I'm not in a position to cancel anybody.
Now you're already canceled. That's how cancellation works.
Interesting. Okay, any questions on
Is
that?
that not too many valence electrons on B though?
On B,
Or I counted wrong?
or which one?
Just the whole thing, the whole structure.
So
No,
if
it's
you-
24.
It's 24?
Yeah.
Let's see.
1, 2, 3, 4,
1, 2,
5,
3,
6, 7, 8,
4,
9,
5, 6,
10,
7,
11.
10, 11, 12, 13.
Yeah, never mind.
17, and wherever else I missed. I clearly missed like 6 electrons, so let's just disregard that. Okay, the formal charge on nitrogen in the compound below is what? Okay. In what situations does formal charge matter more than the octet rule?
Every single situation ever.
Yeah, like all situations, but except when you're dealing with elements in group 2, you have to keep in mind, like nitrogen, you have to keep in mind that nitrogen cannot exceed an octet. Therefore, you cannot put more bonds than it can hold. Therefore, the formal charge rule in that case cannot trump octet rule. But for everything below period 2, formal charge rule trumps octet rule. I don't care what anyone else says.
All just below periods?
Yeah, because period 2 elements can't form. They can't. This is the same for oxygen. It is the same for oxygen because oxygen again is only in group or in period 2, meaning you can only have a maximum of 8 valence electrons, which is why you can't exceed an octet. So again, formal charge rule only trumps octet rule for elements that are below period 2, not including period 2. Makes sense. It makes sense, right? Because you can't exceed an octet on an element that can't afford an octet. Okay. The formal charge on nitrogen is what? 1? Yeah, so that's actually right. So every time nitrogen has three bonds, it's very happy, right? So nitrogen like triethylamine right here. It has three bonds, 1, 2, 3, and then a lone pair, right? That's gonna give it a formal charge of 0.
Use NH3, use triathlon.
Sorry, you don't know your base. So what about, and then here we have 4 bonds, right? And you have to look at the amount of electrons that it owns versus the amount that it should have. So we know it should have 5, and it owns 1, 2, 3, 4. So 5 minus 4 gives us a formal charge of +1. All right, what's the formal charge on the nitrogen in lithium diisopropylamide? Since-
+1.
Wrong. That is wrong.
Why did you?
Which, there's only one nitrogen.
I don't know.
You don't know this, Audie?
-60.
That's impossible.
I knew it was.
Okay, let me give you LBA.
No.
All right, what is the formal charge?
I could use 2.
All right, I wanted to give something that Audie didn't know. He knows everything.
I never said that. I just said I got that answer.
What's the formal charge on nitrogen?
I'm guessing minus. Okay.
But I don't know, He's doing that now.
Let's
So
look at
it's 5 minus.
3 rooms.
He's asking you for another.
Exactly, so in this case, we have.
That's what I
You
said.
said plus,
No, I didn't. I said minus.
Bro.
we can check the
Yeah,
report, okay, we can check. It's gonna be plus, I mean -1.
Which I did minus.
Okay,
Is that correct? There's,
okay,
that would be an
They
H,
did.
right?
So here they're like not.
Oh, yeah.
Figure out.
I can check the.
Three.
Okay, what about, I'll give you all just a couple minutes to do number 8.
Yeah.
How does work has to do with parent? Yeah. Oh. I'm certain. That's not, I have an outcome.
Why didn't you skip out of it? Could have just taken off. Classes.
Hey, same here, let's go.
Aren't you taking a minor?
Wait, what's your major? Oh, me too.
I am on.
You get an answer here, Audie?
Yes.
What
I don't know. Right.
one did you say, Audie? That's pretty- that's-
Called exclusion principle.
That one's just saying electrons can't have the same.
Negative 1 plus 1. There's only 2 quantities over there. Can't have like 2 negative 1, then 1, and 2 negative 1. Positive, I have 3 electrons.
Yeah, you're over.
Tomer, what did you
I
say?
don't know.
You put Hund's rule?
Yeah.
Put
I
Hund's-
also had.
You have to fill up each orbital with 1 before you can double up. That's all it says, but.
Interesting. So the actual answer is Pauli's exclusion principle.
Well.
Okay, so
Like.
because that,
Negative.
so the +1 and minus, the +1/2 for the M sub S. It can either be +1/2 or -1/2, right? This tells us that each orbital can only have a maximum of 2 electrons. Okay. Interesting, huh? Interesting.
Why does it tell us that?
What do you mean? Why it tells us that? Why does it tell us that? Because I don't know.
What?
It just does. This is, sorry, you take OChem 2, you'll know what I mean by it. It just does.
Now, we learned in Gen Chem 2 though.
That's true. We did learn
And
that.
earlier you mentioned that you could have like a thing, like a tetrahedron. You know, and the outside atoms can't bond to each other with the diagonal one. Is that true for anything ever? Or like is that sort of possible?
Oh, I mean,
Like where it like creates that like diagonal bond looking thing.
Yeah.
I mean, you'll see something sort of like that in a class called OChem one.
I'm not taking that.
I know, but there's something called like an epoxide, right? Now epoxide can form bonds like this, and then it can have like whatever else over here. It's kind of weird. They're very reactive because of the strain on the angle effect. All right, how many pi bonds are in this molecule? Pi bonds. Four triple bond.
Each triple bond has
Yes.
2 pi bonds, each double bond is 1 pi bond.
Not four.
Well, oh, the end, there's the end.
Is it four?
Nah. Hey, wait, no,
Look at that.
there's the
Look at
end,
this.
there's the end.
Look at the nitrile group at the very end.
Let's see, yeah.
It's triple
How
bonded,
many,
right?
how many, what is a CN?
So it's
What?
First one.
Triple bond, right?
Yeah.
This
That's.
right here is what we call a nitrile.
Look at this.
And this has C, C, C.
Under the of X squared from 0 to 2, bro.
So a double bond, pi bond, triple bond is two.
A double bond has 1 pi, yeah, and then a triple bond has 2 pi bonds, and that's because every bond has a sigma bond. So a single bond is only composed of a 1 sigma bond. Whereas double bonds have 1 sigma bond and 1 pi bond.
Oh.
Really badly.
Segments. Ah, this makes so much sense.
So 1 sigma plus 1 pi, and then a triple bond would have 1 sigma and 2 pi, for a total of 3 bonds.
So bond broken minus one bond.
Okay. Yeah,
You repeat that like old 10 plus or whatever that is.
oh, that's not 10. It's a sigma, it's a
Oh.
sigma thing. Yeah, I don't know if you've ever seen like the little Figma, I don't know, character, I don't know what's the edge talking about.
Yeah, I don't know
Yes,
if you
it's sigma, it's not 10. So 1 sigma bond and then 1 pi bond for double bonds, and 1 sigma bond and 2 pi bonds for triple bonds. Let's see, we got 1 here, 2. Oh, well, you have to take into account all the hydrogens here.
Oh, you.
So you know what, we're not gonna do that for time's sake. You can do that until. Here's the overachiever of poverty. We like to see it. What is the enthalpy of reaction for the combustion of methane? So remember, you have to know what a combustion reaction is. And you have to know the products that it forms. Good job, Paul.
Oh, sorry.
That's right. Okay, so methane is what? CH4, right? So CH4, and then,
So you just multiply 4 times the CH and 4 times 4.
oh, what is,
times 3.
so first let's write out the balance chemical.
Oh, plus
So what is it reacting with?
O2
O2,
gas.
and it, yes, O2 gas, and it produces CO2 and water. What is the balanced chemical equation here? So we need to put a 2 here, and that would be, we can put a 2 there. Right? Is that balanced? That was balanced. Okay. So we have 1 mole of methane reacting with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water. Okay.
What's the formula?
Oh, yeah. So have y'all learned this yet? Using like bond enthalpy to figure out the, okay. So we're gonna teach y'all now, just because I don't know if y'all's class will cover it with enough time for y'all to get used to it. So delta H of reaction, when we're talking about bond enthalpies, is the delta H of the bond broken minus the delta H of bonds formed.
That's another way of saying delta H of the reactant bonds minus delta H of the product bonds.
But don't get that confused when you do products minus reactants for other scenarios.
So here's a general rule of thumb. If they give you bonds use this formula. If they give you the whole compound, like say they gave you like CH4 itself, use the product mass reactants.
Like if they gave you the enthalpy of combustion for all these separate things, or the delta H of formations, then you would need to do the products minus reactants, right? Because that's for delta H of formations, but they're not giving us delta H of formations, they're giving us the bond energy or. Yeah. All right, so in order to figure this out, we need to see how many bonds are being broken. So we draw methane and we draw our two oxygens, so it'd be two O's. That has a double bond, yes, yeah. And then carbon dioxide looks like this. And then water looks like this. And we have two of those. Okay. So how many, let's see how many carbon hydrogen bonds are being broken here. Are there, well, let's ask, are there any carbon hydrogen bonds on the right side? Carbon hydrogen bonds? So no. Are there any carbon hydrogen bonds on the left side? How many? One, two, three, four. There's 4 carbon hydrogen bonds on the left side, right? Thanks, Michelle. Which means that we're breaking 4 carbon hydrogen bonds. So we'll have to take that into account. So we're going to look at the table. It says that each CH bond has a bond enthalpy of 413 kilojoules per mole. So we would do 413 times 4. All right. So this is just for CHs. How many oxygen double bonded oxygen bonds are we breaking? All right, we're breaking 2, right? Because we have 2 molecules or two moles.
Isn't that supposed to be 3?
Where?
She dies.
Oh, this supposed to be 3.
How would it be 3?
Because they're 6 on the same.
6 on which side?
We balanced it. Okay, sorry, Dylan. I'm sorry. I was excited to.
So. Okay, I'll make a mistake in the future, Maria, so that way you can correct. Okay. So we're breaking 2 oxygen double bond, right? So we look at the table, each of those has a bond enthalpy of 498. So we're going to do 2 times 498. And this is our oxygen bonds, right? All right, so how many, well, let's see, were there any oxygen double bonds formed on the product side? There's no oxygen double bonds, right? So we can continue forward. Are there any carbon oxygen bonds, double bonds formed or broken on the left side? Not on the left side, right? But on the right side, we see that there's 2 carbon oxygen double bonds being formed. All right. So we look at our table, we see that the bond enthalpy of a carbon oxygen double bond is 745 kilojoules per mole, and we're forming 2 of them. So it's going to be 2 times 745. And that is our carbon oxygen double bonds. And how many are we, let's see, on the left side, on the reactant side, are we breaking any oxygen hydrogen bonds? No. What about the right side? Yes. Are we forming? We're forming some, right? How many? 4, right? Because each water molecule forms 2 oxygen hydrogen bonds, and we have 2 water molecules for a total of 4 oxygen hydrogen bonds in form. So 467 times 4. This is our OHs. So we can break this in half. You can say that this is our broken. This is our formed. All right. So if you were to plug all this in, we can transfer it to a neater area so we can understand. So we know delta H of reaction is equal to the sum of the bonds broken, right? So it would be 413 times 4. I'm gonna go ahead and put this in. And then 2 times 498, right? So 2 times 498. I don't have it, but I was. When you have a second, I'll ask you for art. Minus the bonds form. And that was 2 times 745. Okay. And then we add that to the other bonds that were formed as well, which is 467 times 4. So when you finally do all these calculations in a calculator, I'm not gonna do them this moment. But you would finally get it, you should get a final answer of 710.
Negative, right?
Yes. So it's negative 710. And what is our units here? Kilojoule per mole, right? We have, the units are the same as the original units because we didn't change anything. So kilojoules per mole. You have a question?
So when we break a bond, like, whenever we like get together again, like the 12. Well, this is the same energy, like.
I'm sorry. Are you able to, you should pick up just a little bit?
Yeah, so whenever we break a bond, it's the same energy as it takes for.
Oh, yes, yeah. It's, yes, so if you break a bond, it's gonna require 413, like for the carbon hydrogen bonds. In order to break a bond, you have to add energy, so it's gonna be, you add 413 kilojoules per mole. But if you form a carbon hydrogen bond, it's gonna be the same exact amount, it's just opposite in direction. Instead of requiring it, you're gonna release that amount of energy. Okay. Any other, that's gonna be the last problem for today. If y'all don't mind, try to do 11 through 20 on your own time, so that way on Friday we can go over those and I get to compare your answer here.
11 or what, 20?
11 through 20. That's your homework.
I mean, if you want to go above 20 as well,
So,
and
yeah, please feel free to go above 20. I'm gonna just hold you back.
I'd be like certain people, do this review twice. The entire review twice.
All right, please do your little QR code so we can get your attendance for this next exam. We're hoping that the average is even higher on this next exam. Similar to the average on the first exam. Hey, for this exam is not as difficult as the
I'm struggling.
do all the problems.
And then also the matches. So we have to know, remember, like
Only math is.
the bowl, like the wavelength stuff.
Oh, yeah.
Those
That's not that
equations,
bad.
like we've